Hello. In this video, I'm covering section 9.4 on volume and surface area. So we did in the last section, we did perimeter and area. And in this section, we move from the two-dimensional world of lines, polygons, and circles to a three-dimensional world filled with boxes, cylinders, and spheres that are all around us. For example, an artist designing this Bluetooth speaker, the one you see on the left, would be interested in the geometry of three-dimensional solids and surfaces. So we're going to start talking about volume, and it's good to point out that we saw that an area was measured in square units, like square feet or square meters or square inches. And volume is going to be measured in cubic units, like cubic feet or cubic meters or cubic centimeters in cubic units. And we're going to be working with volume. Surface area is still an area. So surface area will still be measured in square units. So I'm going to start with rectangular boxes. Just let's read this paragraph. When we measure length in one dimension, we use units such as inches, feet, and centimeters, and meters. In measuring area in two dimensions, we use square units such as square inches and square centimeters. We measure the volume of a three-dimensional figure using cubic units. So even though we will study three-dimensional objects, we will still measure surface area in square units. So surface area is still an area. I'm going to start with the volume and surface area of a rectangular solid, or sometimes it's called a rectangular parallelepiped. I'm not going to use that term. This is on page 484. So now we have an object in 3 dimensions. Let's suppose we have a rectangular box. With a given length, width, and height. So the volume is a product of length times width times height. And the surface area is going to be the sum of the areas of the 6 sides or 6 faces. Front and back, from this perspective, we see it from this perspective, the area of the front and the back is length times height. So we have front and back, we have 2 times that. Then top and bottom, the area is length times width. We have the top and bottom, we have 2 of those. And left and right, the area of the left and right is going to be width times height. So that's how you find the surface area of a rectangular box. Another way to look at the way we calculated the area for the rectangular solid above is that we multiply the area of the base, which is length times width, times the height h. We can apply this approach to other figures. So in general, and you can see this figure. I want to make sure that I'm sharing. I'm pretty sure I was sharing. Just making sure. If we look at this figure, 9.7, the volume when the object has a flat top base and size perpendicular to the base, and the area of the base is A, and the height is H, the volume will be area of the base times height. So that's on the same page. 484. So if an object has a flat top and base, so let's say you have some object. Then you have something like that. Okay, so let's say that the area of the base is A. Or I'm not going to do that. But we have some type of object. Let's say that the area of the base is A, and the height is H. So the volume is area of the base times height. Or the formula that you see above is A times H. We're going to go over example 1. In the figure below shows 2 blocks of cheese that are selling for the same price. So which block contains the greater volume, or which one should you buy? Which one is going to be a better, is going to give you better bang for your buck? We're going to use the formula to find the volume. That is, we're going to find the area of the base. The first one is a trapezoid. The second one is a triangle. We're going to find the area of the base, multiply by the height, and compare the volumes. So let's start with the first block, or let's call it the trapezoidal block. The area of the base so that's a trapezoid, and we saw that the area of a trapezoid is 1/2 times lower base. The lower base is 9, the upper base is 5, and the height of the trapezoid is 3. 9 plus 5 is 14. So 1/2 times 14 is 7. 7 times 3 is 21. The volume is going to be 25 square inches. And that one is a 1. And the volume of the block is going to be the area of the base times the height. So the volume is 21 times 4, or 84 cubic inches. And we're going to compare this to the triangular block. Okay, the triangular block. We know the length of the sides of the triangle that forms the base. So we cannot use the formula 1/2 times base times height. We need to use Heron's formula to find the area of the base. Okay, when we use the Heron's formula, the sides are 9, 9, and 6. So we need to compute this constant. That's 1/2 times 9 plus 9 plus 6. And that is 9 plus 9 plus 6 is 24. 24 times 1/2 is going to be 12. The area of the base is going to be S times S minus 9, S minus 9, and S minus 6. So that is 12 times 3 times 3 times 6. The square root of 12 times 3 times 3 times 6, which is equal to 684. And the volume of the block is going to be the area of the base times the height, which is 3. So that's going to be 3 times, that is 3 times of the height times the area of the base. When we multiply that, that's going to be, let's see, let's compare. Well, what we have is the, well, we were going to have the volume, so let's compare. 684, the square root of 684 times 3 is approximately 78. Okay, just making sure for some reason I have a different answer in my notes. So let's compare. Okay, that's 648. That's why. Yeah, so I'm going to correct this. So that's 648. And we're going to fix this in the notes. Okay, so the volume is going to be that times 3. So that's the square root. And then multiply by 3. That's approximately 76.4 approximately. And that was in cubic inches. Okay, so let's compare the volumes. That was the volume of the triangular block. And the trapezoidal block has, the volume of the trapezoidal block is 84 cubic inches. So the trapezoidal block has more volume. And that's the one you should buy. You're going to get more product for the same price. Okay, the next type of figure. So we have done rectangular boxes, figures with a flat top and bottom that are parallel to each other or whose sides are perpendicular. The next type of figure are going to be cylinders. Okay, so in a cylinder, let's say we have a cylinder, a right circular cylinder. That is the base of the cylinder is a circle with radius r. And height h. The volume is still going to be, it still has a flat top and bottom, and the sides are parallel. I mean, the sides are perpendicular to the base. So the volume is still going to be the area of the base times height, but the area of the base is pi r squared. So it's going to be pi r squared times height. And the surface area, I'm not going to go over the details, but to obtain the surface area, you can do that by cutting the cylinder and then flatten it. So the area of the sides is going to be 2 pi RH, and I'm just going to copy the formulas. Okay, so a right circular cylinder with radius r and height h has volume pi r square h and surface area 2 pi RH plus 2 pi r squared. I'm going to go over example 2. Involving the volume of a cylinder. An art supply store sells paint solvent in a cylindrical can that has a diameter of 4 inches and a height of 6 inches. The giant economy size can of the same solvent has a diameter twice as large and costs 3 times as much as the smaller can. The heights are going to be the same. Okay, so we have 2 cans. We have the standard size, that has a diameter of 4 inches and a height of 6 inches. And the giant economy size has a diameter twice as large. So the diameter is going to be 8 inches and the height is the same. Actually, what I drew was the radius. They give us the diameter. So that's 4 inches. That's the diameter and not the radius. And it's the same height. Okay, we're going to find which can is a better deal. Knowing that, the giant economy size costs 3 times more. Or 3 times as much. Okay, so what we're going to do to determine which one is the better deal, we're going to compare the volumes. So if the giant economy size is or gives you more than 3 times as much product, then that one is going to be the better deal. If it gives you less than 3 times as much product, the standard size is going to be a better deal. It's going to be better to buy 2 or maybe 3 of the standard size. Or 3 of the standard size, because that's going to be the same price and that would give you more volume. Okay, so let's find the volume of the standard size. If the diameter is 4 inches, the radius is 2 inches. The radius is 2 inches, and the height is 6 inches. So the volume, it's pi times r squared times 6. Pi is approximately 3.14. Two square is 4. 2 square is 4, so that's going to be 3.14 times 4 times 6. And that is equal to 75.36 cubic inches. And the giant economy size has a diameter of 8 inches. So the radius is 4 inches. And the volume it's pi times 4 squared times 6. That's approximately the approximate. Pi is approximately 3.14. 4 squared is 16 times 6. And this is 301.44 cubic inches. Okay, so we're going to take the ratio to determine which one is the better deal. This is 301.44 over 75.36. So at the end, that's going to be equal to 4. And with that in mind, so the volume of the giant can is 4 times the volume of the standard economy size, but costs 3 times as much. So that one is going to be the better deal. Let's type this. The giant economy size can is the better deal. Because it has 3 times as much volume. It has 4 times as much volume, but it is 3 times more expensive. Or costs 3 times as much. And we have another question. The other question is to compare the surface areas of the 2 cans. And that's important for the manufacturer. That tells the manufacturer how much material I mean, how much material does he or she needs to build those cans. So yeah, that's also important. Okay, so let's compare the surface areas. Okay, so the surface area of the standard size is going to be, remember the formula? The formula for the surface area is 2 pi RH plus 2 pi r squared. So for the standard, that's going to be 2 times. Pi is approximately 3.14. The radius is 2. The height is 6. Okay, let's compare the surface area. Remember, the surface area is still an area, so it's still going to be in square units. So this is 2 times 3.14 times 2 times 6 plus 2 times pi times 2 squared. That's 100.48 square inches. And we're going to compare this to the volume of the giant economy size can. The surface area is 2 times pi times radius times height plus 2 times pi times square of the radius. Okay, so that's 2 times 3.14 times 4 times 6 plus 2 times pi times square of the radius. So that's 251.2. So if we take the ratio, the ratio is going to be 251.2 over 100.48. And that's going to be 2.5. Yeah, so that's also important for the manufacturer because it has more volume, but it takes less material. I mean, the manufacturer is selling the product or is selling the giant can for 3 times as much, but it takes only 2.5 as much material to manufacture. And the last type of figure, the two figures, the last two are going to be constant spheres. So we're going to start with a right circular cone. Okay, so let's say we have a right circular cone with a given height and base radius. So the base of the cone is a circle with radius r, and the height of the cone is h. The volume of the cone, and I'm not showing you the formula because, well, I'm not proving the formula because it's not as intuitive as the ones we did. The volume is 1/3 times pi times r squared times h. And the surface area is pi times the radius times the square root of the square of the radius plus the square of the height. So the next example is number 6. We're going to use the formula to find the volume and surface area of the cone. This is number 6 on page 490. Okay, so there it is. The cone has radius 5 meters and height 18 meters. Okay, so let's do the, okay, we know the radius and we know the height. So the volume is 1/3 times pi times the square of the radius times the height. Pi is approximately 3.14. The radius is 5. And the height is 18. Okay, so I'm going to put this in the calculator. This is 1/3 times pi, or you can use the bottom pi if you want. My MATLAB is going to accept it. Either way, so my MATLAB is going to accept both answers, whether you just type 3.14 or whether you use the pi button, my MATLAB is going to accept it. Okay, so times square of the radius times 18. And that's going to be exactly 471. So that's going to be 471 cubic meters. And the surface area is pi times the radius times the square root of the radius plus the square of the height. That's approximately 3.14 times the radius times the square of the radius, the square root of the square of the radius plus the square of the height. Okay, so I can just go ahead and plug it in like that. So this is 3.14 times 5 times 5 squared plus 18 squared, square root of that, and that's going to be approximately 293.3 cubic meters. Okay, the last type of figure is going to be a sphere. Okay, so that's the last, those are the last two formulas. Okay, so let's say we have a sphere with radius r. So the radius is going to be the distance from the center to any point of the sphere. The volume is 4/3 pi r cubed, and the surface area is 4 pi r squared. Okay, so let's do an example of this formula. We're going to find the volume and surface area of the sphere. So we're doing number 4. Okay, the volume of the sphere is 4/3 times 3.14 times 5 to the third power. Let's calculate that. This is 4/3 times the radius times pi. So you can use the pi button. And my MATLAB, again, my MATLAB is going to accept it. So you can also do that times the square of the radius. And that's approximately 104. Okay, I'm missing something. Actually, that should have been to the third power, not to the second power. So let's start again. So that's 4/3 times pi times 5 raised to the third power. So that's about 593.6 cubic inches. And the surface area, it's 4 times pi times square of the radius. Okay, so let's do that. This 4 times pi times the square of the radius. So that's about 314. So we're going to approximate this to about 314. That's surface area, so that's going to be in square inches. And actually, this one were square meters because that's an area. So those are square meters. Those are not cubic meters. Just fix that. And finally, I'll do an application. So that's number 17 on page 490. A punch ball is in the shape of a hemisphere with a radius of 9 inches. The cup part of the ladle is also in the shape of a hemisphere with a radius of 2 inches. If the ball is full, how many full ladles of punch are there in the ball? Okay, so we're going to find the volume. We're going to find the volume of the ball. So it's in the shape of a hemisphere. The radius is 9 inches. So the volume, so it's going to be half of a sphere. This is going to be 1/2 times 4/3 pi r cubed. And it's 1/2 because it's a hemisphere. So we can simplify 1/2 and 4/3 as 2/3. Okay, so the volume of the ball is going to be 2/3 times pi times the radius plus 9 cubed. Let's verify this. And that's 1526.04. That's in cubic inches. And we're going to find the volume of the ladle and then take the ratio. Okay, so the cup part of the ladle is also in the shape of a hemisphere with radius of 2 inches. So that's going to be the radius. So the volume is going to be 2/3 times pi times 2 to the third power. So that's about 16.75 approximately. And to answer the final question, how many full ladles of punch are there in the ball? We're going to take the ratio. (1,526.04) divided by 16.75. So we're going to, let's see. Chances are that if we have a decimal, we're going to round down. This is 1,526.04 divided by 16.75. And that's about 91. That's approximately 91. It's going to be a little bit more, but we're going to round down to the greatest integer. So there are 91 full ladles in the bowl. Okay, so this is it. With this, we have covered section 9.4. Thank you for listening.